Okay, so we're going to look at the second fundamental theorem of calculus again in this lesson. We're going to extend what we learned in the previous lesson. In the previous lesson, we were doing a very basic part of the second fundamental theorem, but we're going to extend that a little bit today to our chain rule. And so the second fundamental theorem of calculus basically says if f is continuous on the closed interval a to b, and u of x and v of x are some differentiable functions of x whose values lie within a to b, then our chain rule says if I want to take the derivative, so that's what this notation over here on the left is saying, taking the derivative of the integral, and again, where u of x and v of x are some functions, 2x or cosine of x or whatever, taking the derivative of an integral f of t dt equals, now this is similar to what we did in the previous lesson, but in the previous lesson we took this upper value and we simply plugged it in and we were done. That's because that upper limit was x. Now we're still doing the same thing. Notice over here on the right side it says f of v of x. So we're still going to substitute in the upper limit. So I'm going to make a couple little notes here. Substitute, upper limit, and then right next to that you'll notice it says dv dx. That's the derivative of the upper limit. So then we're going to multiply, okay, basically what that's saying is times the derivative of the upper limit. All right, so we're going to substitute in that upper limit. We're going to multiply that part by the derivative of the upper limit, and then we're going to subtract, just like the fundamental theorem says, f of b minus f of a. Okay, very similar. And then we're going to substitute in the lower limit. So we're going to substitute lower limit. And then right next to that, you'll notice it says du dx. So we're going to times the derivative of the lower limit. All right, derivative of lower limit. Okay, so let's take a look and see how this works. If you look at the example below, we're going to start off a nice easy one here. It says that the function f of x is given by the integral pi halves to x cubed of cosine t dt, and we want to use this to find f prime of x using the methods below here. Okay, did I miss one in here? Okay, for some reason I missed an example from the notes somewhere in here. Interesting. All right, well, we'll skip that first example in the notes. Let's take a look at this one. All right, so this is down, this looks like it's actually example 2 here. Give me 1 second here. Okay, no, we're good. We're good. I was looking at an old set of notes here. So, all right, so it says use the function to find the derivative f prime of x using each method below. So the first way we can do this, if you ignore what we just talked about right up top, if I want to find f prime of x, there's actually 2 ways I can do this. I can start off by integrating first and then taking the derivative. Because if f of x is an integral, I could actually solve this integral, and then after I solve the integral, I could take the derivative of that equation and find f prime of x. So I'm going to do that first just to show you how this works here. All right. So if we start on the right-hand side of this, so I'm not even going to worry about f of x right now, okay? So f of x is equal to the integral. So let's just find the integral. Well, the integral of cosine t is sine of t. And we would evaluate that integral from pi halves to x cubed. And according to the fundamental theorem of calculus, we would simply plug those values in. So this would be sine of x cubed minus sine of pi halves. And so now we could, we can evaluate sine of pi halves. I'm going to go one step further here. So this would be sine of x cubed minus, and sine of pi halves is just 1. Okay? So now what we're saying is we're saying that f of x is equal to the sine of x cubed minus 1. And what we want to find is f prime of x. Okay, so now I want to take the derivative of both sides. So f prime of x, if we go to the right side, the derivative of sine is cosine of x cubed times the derivative of x cubed, which is 3x squared, and then minus the derivative of 1, which is at 0, so we really don't need that there. So f prime of x is 3x squared times the cosine of x cubed. Okay, so that's one way to do that. You can simply integrate first, then take the derivative. Now, in method number 2, I'm just going to apply the second fundamental theorem of calculus, which is what we talked about up here, where it said, look, plug in the upper limit, take the upper limit, plug it in for t, multiply by the derivative of the upper limit, then plug in the lower limit, multiply by the derivative of that, and subtract that from the first part. That's what we're going to do in this second method here. So in the second method, really, again, what we're saying is, look, take this upper limit, so f prime of x, so we're going straight to the derivative here. F prime of x is equal to, we're going to plug in the upper limit, that's cosine of x cubed. Cosine, there we go, of x cubed. And then we're going to multiply by the derivative of x cubed. So the derivative of x cubed is 3x squared. And then we're going to subtract, and we're going to plug in the lower limit for t, which is cosine of pi halves. And then we're going to multiply by the derivative of pi halves. Well, pi halves is just a number, so the derivative of pi halves is 0, and we end up with f prime of x equal to 3x squared times cosine of x cubed minus 0, which is exactly what we got in that first example. Here's the thing. Sometimes you can do method 1, but we can't always integrate, so method 2 tends to work better. Just plug in each limit, multiply by the derivative of that limit, and then subtract. Take a look at example number 2 here. We're going to do fundamental theorem of calculus. F prime of x is equal to, here we go with the upper limit, plug in, this is cosine of e to the x squared times the derivative of x squared, so that's 2x, minus, plug in the lower limit of 3 cosine of e to the third power times the derivative of 3, which again is 0, and we simply end up with f prime of x equals 2x times cosine of e to the x squared. Okay? All right, let's see what we got next here. All right, so when it says find f prime of x, it tells us that f of x is the integral. Okay, so f of x is the integral, find f prime of x. So I'm going to take x and I'm going to plug it in wherever I see t. So this is going to be f prime of x equals 1 over x. Now I need to multiply this by the derivative of the upper limit, so that's times 1, minus, now we're going to plug in the lower limit for t. Now this one's going to get a little bit funky, so I'm going to write it out the first time, but you'll see what happens here. So I have 1 over x times the derivative of 1 over x. Now, what's the derivative of 1 over x? Okay, and in order to do that, you have to know that 1 over x is equal to x to the negative 1. And so if I take the derivative of x to the negative 1, I would get negative 1 x to the negative 2. So that's the derivative that I need to multiply by, times, actually I'll do it like this, times negative 1 x to the negative 2. Now we should simplify a little bit along the way here, so we're going to continue to go here. So my first blue part in blue there is just 1 over x. And this is going to be minus. Now I'm multiplying by a negative, so this will actually turn plus. 1 divided by 1 over x is just x. And I've already taken care of the negative 1 here. And then I have x to the negative 2, which is going to go down to the bottom, times 1 over x to the positive 2. You can cancel a couple of these x's here. So you end up with 1 over x plus this. When you cancel here, this leaves, the 2's gone, it leaves another 1 over x, and I end up with 2 over x, and that one's done. Alright, let's take a look at the one on the right side. If h of x equals this integral, find h prime of x. Alright, so h prime of x. The first thing I'm going to do is I'm going to plug in sine x for t, right there. So this is going to equal 1 over 1 minus sine of x. And you could write sine squared of x or sine of x squared times the derivative of sine. Okay, so remember the second part of the fundamental theorem says now take the derivative of the upper limit. Well, the derivative of sine is cosine x. Alright, you're going to subtract. Now we're going to go and plug in the lower limit for t. So that's 1 over 1 minus cosine of x squared, and then times the derivative of cosine, the derivative of the lower limit, which is times, and actually I'm going to do this one in parentheses because it's negative sine x. Alright, now we can do a little bit of simplifying here, I think, because let's see here. Think about your trig functions here. H prime of x. Now again, this bottom part could be 1 minus sine squared x. Well, 1 minus sine squared x is cosine squared x. So this whole bottom piece under here, this dude right here is cosine squared x. So what I have is I have a cosine x on the top, a cosine squared x on the bottom. So I can do a little bit of canceling there. And the same thing happens on the right. 1 minus cosine squared x is sine squared x. So I end up with, well, now we got a negative negative again, so it's going to be plus. So I have sine x over sine squared x. And that whole thing, cosine over cosine squared is just cosine x. Sine over sine squared is sine x. And that's all you got right there. Okay? So sometimes you can simplify a little further than you think. Alright, let's take a look at this next one. Okay, I got to pay particular attention on this next one because now I've got a square root. So I know that the square root of y is equal to y to the 1/2. Because I'm going to have to take a derivative of that in just a minute. So I may actually, I won't rewrite it. I'm just going to keep in mind that the square root of y is y to the 1/2. So g prime of y is going to equal, and again, the first thing we're going to do, and you know what, I am going to change this integral. I think it'll be easier to see. So I'm going to go back and I'm going to write g of y. So g of y equals the integral from 2y to the 1/2 power over y to the 1/2 of sine t squared dt. Alright, so now I'm going to plug in. I think it'll just be a little bit easier. So g prime of y is equal to plugging in 2y to the 1/2 for t. So this is going to be sine of 2y to the 1/2 squared times the derivative of 2y to the 1/2. Now you got to be careful here, because I mean the derivative of that, when I bring the 1/2 down in front, the 2 is going to cancel out, and that's going to leave me y to the negative 1/2 minus, now I'm plugging in the bottom part, y to the 1/2 for t squared, so that's going to be sine of y to the 1/2 squared times the derivative of y to the 1/2, which is 1/2 y to the negative 1/2. Okay, so we could do some simplifying on that, but I think we're just going to leave it alone for now. Okay, well, we got a little bit of room here. Let's see what we got. So this would be g prime of x equals, now when I square 2y to the 1/2, I got to square 2, which is going to be sine of, oops, I wrote x, but I needed y back here. G prime of y. So this is going to be sine of 4 y to the 1/2 squared. You multiply the exponent, you get 1, so that's sine of 4y. We have y to the negative 1/2, which means that's going to drop down to the denominator. And I could actually, when I drop it, I could write it as y to the 1/2, or I could write it as the square root of y. Minus, now the same thing is going to happen over here. I've got sine of y to the 1/2, but I'm going to square the y to the 1/2. So that's going to be sine of y. And notice my y to the negative 1/2 is going to drop down again, so this time I've got 2 times the square root of y in the denominator. Alright? And you can't combine those, they're not like terms or anything like that. Alright, next one. Alright, I'm going to rewrite this one for sure. This is f of x equals the integral from 3 to 2x of t squared plus 1 to the 1/2 power dt. We're supposed to find f prime of x. So f prime of x, again, all I'm going to do here is plug in 2x for t. So this is going to be 2x squared. So I might need another set of parentheses out here. Plus 1. And that whole thing is raised to the 1/2 power. So that's just plugging it in. Now I have to multiply this by the derivative of the upper limit, so that's times 2. Then I'm going to subtract, and I'm going to plug the lower limit in, and the lower limit's 3. So this is going to be subtract 3 squared plus 1. And actually I need some parentheses here, because this whole piece, you know what, I don't need them right there, that's okay. I need them on the outside. 3 squared plus 1 to the 1/2. Now times the derivative of the lower function, so that's going to be times 0, because derivative of 3 is 0. And so f prime of x is simply going to be, and I'll do a little bit of simplifying along the way here, this is going to be 4x squared plus 1 to the 1/2 times 2. Alright? Not so bad, is it? Alright, let's flip over to the next page. Alright, it says let f be the function that is continuous and differentiable on the interval 0 to 8. So you can see f of it, or we got f and we got g here. Oh, okay. F of x is a function that is continuous and differentiable on the interval 0 to 8. It's defined by f of x equals the integral from 0 to x of g of d dt. The graph of g is the piecewise function shown at the right. Now, you got to think here, because again we're dealing with x's and t's here, and so when they say to find f of 1, whenever I'm asked to find f of 1, if I've got a function, I'm going to plug that into the function. So f of 1, I'm going to do that one here, f of 1, my function's already defined for me, so that's going to be, when I plug in 1 to the function for x, I'm going to get 0 to 1. So you'll notice it was 0 to x before, okay, but when I plug in 1 for f, now I need to change that x and go from 0 to 1 f of t dt. So in other words, what they're telling me to do is they're telling me to find the area under the curve from 0 to 1. So I come over here, I go to 1, and what I'm looking for here is this little area right in here. Well, that's pretty easy because I can do that geometrically. So this is going to be 1/2 times the base, which is 1, times the height, which is 1, 2, 3. So that whole thing's going to equal 3/2. Okay? So that's what they mean when they say find f of 1. You just plug in 1 for x just like you normally would. And then you don't have to worry about, you know, using the x in the upper limit here to plug in and multiply by the derivative and all that kind of stuff like we were doing on the other page. All right? F prime of x. So now they want us to find f prime of 1. In order to do f prime of 1, I need to know what f prime of x is. Okay? So I'm going to change colors here. We'll do f prime of 1. Okay, so I need to know what f prime of x is before I can do this. This is going to be the integral, so we should actually say d dx of, where is it? The integral from 0 to x of g of t dt. Okay, and so when I go to do this, I'm taking the integral of, well, first of all, I got to do g prime of t, right? So I've got to make sure that, according to the second fundamental theorem of calculus, so to do this, we're going to plug in our upper limit. We're going to plug in x. So this is going to equal g of x. And then I need the derivative of the upper function. Okay, so the derivative of x is 1. So that's g of x times 1 minus, and then we take our lower limit, we plug it in for g of t, and so that's g of 0 times the derivative of 0, which is 0. We get a lot of stuff canceling out here. Alright, so this is just a function, and you can see that the whole second part here is going to cancel out here. So all I have left now is g of x. So f prime of x is equal to g of x in this case. So if I want to find f prime of 1, go back to red here, f prime of 1, that's just g of 1. And so if I go over to my function right here and I look where x is equal to 1, well, when x is equal to 1, g is equal to 3. So that whole thing turns out to be 3. That wasn't so bad, was it? Alright, now I need f double prime of x. So f double prime of x, because now we're going to do f double prime of 1. So f double prime of x is going to equal, now if you think about it, if f prime of x equals g of x, okay, so we just showed that back here, f prime of x equals g of x, then f double prime of x should equal g prime of x. Hopefully that relationship makes sense there with what I highlighted up above. So now I need to do f double prime of 1, which is going to equal g prime of 1. So what I'm asking for now is what's the slope on the function g when x is equal to 1. So, okay, so here's my point again. There's x equal to 1. I need to know the slope at that point. Well, that point is on a straight line, and that straight line has a slope of 3. So f double prime of 1 equal to g prime of 1 equals 3. All right? So I would encourage you at this point to turn off the video and try and do letter B, because it's going to be the exact same thing. You're just going to be using a different number. You're going to be using 2 instead of 1. All right? And see what you can come up with on that. All right? All right, so f of 2. f of 2 is going to be equal to. Now, because I've got my function up here at the top, all I need to remember is that, first thing I need is f prime of x, but I guess I'm skipping some steps here because we already did f prime of x back up here in part A. So I know that f prime of x is equal to g of x. So I know that f of 2 is, I'm one step ahead of myself here. All right, let me back up a second here. So on to part B here, I need to find f of 2. So if I plug in 2 for x, I would have f of 2, and now I'm plugging into the integral up here at the top. So I'm taking the integral from 0 to 2 of g of t dt. So now they want the area for all the way to 2, so I'm going to scratch, and so now we'd have this integral all the way over to here. Alright, so I'm going to do, this is a triangle again, so 1/2 times the base. The height this time is 6, and we end up with f of 2 equal to 6. F prime of 2, now we already did the derivative for f prime, and we showed that f prime of x is equal to g of x. So f prime of 2 is equal to g of 2. And again, this graph over here is g. So if I look at this, g of 2 is defined right up here at 6. So this is equal to 6. And then f double prime of 2 is equal to, and again we showed that f double prime is equal to g prime. So this is g prime of 2. So if I go to 2 again, now I'm going to erase a little bit here just to make things a little more obvious, but if I look at this point up here at 2, okay, g of 2 is defined. We just showed that in the previous step. We know that g of 2 is equal to 6. However, g prime of 2 is saying give me the derivative when x is equal to 2. And the derivative at that point does not exist. G prime of 2 does not exist because, and if you remember your limits here, the limit as x approaches 2 from the negative side of f double prime of x. So what we're saying here is the slope on the left side, okay, of that line does not equal the limit as x approaches 2 from the positive side of f double prime of x. Okay, the non-mathematical term is sharp turn, but the sharp turn. But the mathematical reasoning is that the limit of the derivative does not exist on both sides of the number 2. All right. All right, so letter C says, is x equals 6 a maximum or a minimum of f? Okay, so we know that let's see here, is x equals 6 a max or a min? So when we talk about this, we're looking at x equals 6 is a max because, let me see, f prime of x equals g of x, and f prime of x goes from positive to negative at x equals positive 6. So basically what they're saying is this. If you look over here on the graph, this is x equals 6 right here, that point that I just put on the graph. Now, how do I know that that's a max? Because when we talk about g of x up here, we know that g of x is, this graph is not only g of x, but it's f prime of x. And if f prime of x goes from positive to negative, that means that f goes from increasing to decreasing, and therefore that point would have to represent a maximum of f of x. Okay? How many points of inflection does f have? Explain your reasoning. Okay, so might need to look at our graph again here. So we want to look at where f, let me see, points of inflection does f have. So when we talk about points of inflection, we want to know where f double prime is 0, or we want to know where f prime goes from increasing to decreasing. So again, your graph up here is f prime, and if you look at the number 2 right here at x equals 2, f prime goes from increasing to decreasing, which would imply that f double prime goes from positive to negative, therefore creating a point of inflection. So f has one point of inflection because f prime goes from increasing to decreasing at x equals 2. Now the part that you don't need to say but that's implied then is that this implies that f double prime goes from positive to negative. Okay, so f prime goes from positive where f prime is increasing, f double prime goes to negative where f prime is decreasing, which implies that f has a point of inflection. Okay, so the part in the green you don't really need. The part that talks about f prime going from increasing to decreasing is enough. All right, what is the equation of the tangent line of f at x equals 1? Well, for any tangent line we need a point. All right, so I need a point at 1. So I need to know what f of 1 is. All right, so I definitely need to know that. And I think we already did that back here up at the top. So we should have our point already. Okay, so let's see what our point is. F of 1 was equal to 3/2, way up here at the top, 3/2. We already did that back there. We have a point, 1 comma 3/2. We need a slope. All right, so we need to know f prime of 1, and we should have done that back there at the same time. F prime of 1 we said was equal to 3, so there's our slope. So once we have a point in the slope, it's just a matter of plugging it in. Y minus 3/2 equals 3 times x minus 1. And that's the tangent line at x equals 1. All right? Okay. Looks like I missed a letter here, but I'm not sure. Maybe it's a new problem. Let's read it. What is the value of x that maximizes the value of f of x if f of x equals the integral from x to x plus 3 of t times 5 minus t d of t? All right, so I think what we have going on here is when we talk about maximizing a value, we're talking about where the derivative is going from positive to negative, where your graph is going from increasing to decreasing. So in order to do that, we need to find the derivative and find critical points for the derivative. Okay, so the first thing I'm going to do is I'm going to look for f prime of x. F prime of x. So again, this is the second fundamental theorem of calculus, and what it says is we take the upper limit and we plug it in for t. So I'm going to have x plus 3 times, and we're going to do 5 minus. Now I got to be careful here. I should use some square brackets here. 5 minus, x plus 3. So that's plugging in x plus 3 for t here and here. And now we need to multiply that by the derivative of the upper limit. But the derivative of x plus 3 is just times 1. So I'm going to put it in there so you can see it. Then we're going to subtract. And now we're going to plug in x for t here and here. So we have x times 5 minus x. And then times the derivative of the lower limit, but that's just times 1 again, so hopefully that makes sense. All right, we can clean this up a little bit because we can't leave it like this. So we have f prime of x, and we have x plus 3 out here. On the inside we have 5 take away 3, which is going to be 2, and then minus x. And then we're going to subtract, and we're going to distribute the x in there, so that's going to be negative 5x, and then plus x squared. And I still need to clean up the front end here, so f prime of x, we're going to FOIL these guys together. That's going to give us 2x minus x squared plus 6 minus 3x. Kind of a weird way to FOIL, all out of order there. Minus 5x plus x squared. Alright, so now that we have everything multiplied out, I notice that the negative x squared here and then positive x squared here cancel out, which is going to make this a little bit easier. So f prime of x, and I'm going to try and put this in order as we simplify here. So we have 2x, and then we have minus 3x, which is negative x, minus 5x, which is negative 6x, and then the only other number left is plus 6. So this is our derivative, and again we're talking about the value of x that maximizes the f of x. So what we're talking about is critical numbers. Okay, so again, critical numbers, that's where f prime is undefined, and in this case you can see we don't have any because it's just a polynomial, and where f prime is equal to 0. Alright? So I'm going to take my derivative and I'm going to set it equal to 0. So I'm going to get 0 equals negative 6x plus 6. If you add 6x to both sides, you get 6x equals 6, and divide out the 6, and you get x equals 1. So I only have one critical value. Alright? So I'm going to set up my number line just like we always do. And we're going to put 1 here. This is f prime of x. It's going to tell us what f of x is doing. So I'm going to try, let's see, to the left of 1 I'm going to do x equals 0 and x equals 2. So again, I'm plugging this into f prime, and f prime is this equation right over here on the left side. So if I plug in 0, that first part goes away, negative 6 times 0, that's gone, so plus 6, so this is going to be positive. If I plug in 2 to that same area, I get negative 12 plus 6, so this side's going to be negative, which tells me that f of x goes from increasing to decreasing at positive 1. Okay, so we would say that f has a max at x equals 1 because f prime of x goes from positive to negative. Alright? That was fun, wasn't it? Here you go. Have fun with that one. Alright. See you on the next round.